I'm a PhD student at New Mexico State University and working on quantum error correction. Today, I'm going to talk about quantum LDPC codes with linear distance and linear dimension. Finding quantum codes with linear distance and linear dimension is an open problem in quantum error correction. And in this work, we introduce some quantum codes with linear distance and linear dimension. Here's a brief overview of the topic. First, we look at the quantum codes can be constructed from the product, including balance product and the chain complex. Then I will show an example to illustrate this concept. I also cover the main theoretical result and finish with a discussion on the simulation outcome, giving a picture on how quantum LDPC codes can achieve better performance. And quantum LDPC codes are designed with two primary conditions. First, each check operates on the constant number of the qubits. And second, each qubit is involved in a constant number of the check. These codes are represented with the three key parameters: n, number of physical qubits; k, the number of encoded or logical qubit; and d is the lowest weight of the logical operator. The aim is to balance these parameters for optimal error correction. In this slide, introduce product construction, a technique used to create quantum LDPC codes. Product construction combines simpler codes to the more complex structure, allow us to achieve durable properties like better distance and dimension. This method is a fundamental for building quantum LDPC codes that meet the strict requirement of quantum error correction. If we consider two classical codes and then calculate the product between them, we can see that we have a quantum code, or in the torus code, torus curve. And Z check and Z operator defined by in the edges and vertices in the torus. Here we have a quantum hypergraph product code. If we consider two classical codes with linear distance and linear dimension and then calculate tensor product between them, we can see that we have quantum hypergraph product codes. In quantum hypergraph product code in this structure, we can see that the distance is linear, but the dimension is not linear yet. And also, we have a figure of this product construction. If we have a two classical codes that as we have here, as there, we check and bid and then calculate the tensor product or hypergraph product of this code, we have this quantum code that a physical qubit defined by edges and X checks and Z checks defined by vertices. Two-set product construction add another layer of complexity by introducing two-state in the product structure. This approach allows us more flexibility in the design and leading to codes with enhanced error correction capacities. Two-set product play a significant role in optimizing the structure and performance of quantum LDPC codes. With two-set product construction, we have a larger minimum distance. Minimum distance in the torus defined with a cycle. The shortest cycle in the torus curve is the minimum distance. But in this curve, we can see that is a two-set product construction. We can see that our minimum distance is larger, and it's a good achievement for quantum error correction. And the balanced product involves two topological space, X and Y, with a group acting on each. In this context, we use an anti-diagonal action to form the balanced product. This balance approach is valuable for construction quantum LDPC code because It maintains code structure while introducing group symmetric that help manage cubing check effectively. My construction in my work use the balanced product construction for building a quantum LDPC code. With this balanced product, we find the linear distance and linear dimension in the result. And we have another definition of the chain complex. Chain complex is one of the concepts that used in the quantum LDPC code. Consists of the vector space connected by a linear map. That each map one space to another and satisfies a condition called squaring to 0. For example, here we have delta I minus 1, delta I is 0. This is a main condition of the chain complex that we must have. And also we have another definition and concept in the chain complex as I cycle, I boundaries, and ice homology, that we can find the parameter of the quantum code using this concept. And I have an example. I will show how we can find quantum code parameter using this concept. And we can find the quantum code from chain complex if we consider three category in the chain complex. For example, C1, C0, and C minus 1. We have three category and we define the chain complex. Before I explain the quantum code from chain complex, I want to mention that if we have only two category, for example, C1 and C0, we have classical codes. And we define delta 1 as a parity check matrix for the classical code. But if we have three categories, C1, C0, and C minus 1, we have quantum codes. That delta 1 is a HX matrix, parity check matrix of the Z check. And delta 2 is HZ transpose Z check matrices for quantum codes. And the number of qubits calculated by the dimension of the main category of the chain complex. And the dimension is calculated by K is calculated by dimension of H or I homology. Also, finding the parity check matrices HX and HC is a challenging part in quantum error correction, also for CSS construction in the quantum error correction. For chain complex, we have delta 2 and delta 1. For delta 1, we have a matrices that row is represented by faces and column represented by edges. And if we have a relationship between faces and edges, we put 1, otherwise we put 0. We have some construction for delta 1. That means that if the column represent with the edges and the row represent by vertices. And again, if we have a relationship between edges and vertices, we put 1, otherwise we put 0. From the main condition of the chain complex, we know that delta 1, delta 2 is 0. And from this, we can see that HX, HC transpose is 0. That is, we have valid CSS code and quantum code from chain complex. We have a definition of the Cayley graph here. Cayley graph defined by group G and generator S. That vertices comes from group G and edges comes from generator S. Also, we have two examples of the Cayley graph with generator Cayley graph Zn with generator 1, and also Cayley graph Zn2 with generator E1. I use the concept of the Cayley graph and the balance product to find new quantum LDPC codes that have a linear distance and linear dimension. Here, an example of this construction, we consider two Cayley graphs, Z6 and Z3. And here we constructed the balance product between Z6 and Z3 by Z3 the main. Using this balance product, we have this graph for this balance with this construction. That is, we define delta 1 and delta 2 as here. As I mentioned before, delta 1 is Hx and delta 2 is Hc transpose. From the definition of the quantum code from the chain complex, we have that the number of qubit is the dimension of the main category, that is 12. And another way to finding the number of qubit, we must look at the graph. The number of edges is equal to number of qubit. We have totally 12 edges and the number of qubit is 12. Also, we have the minimum distance here for the quantum code. For the finding the minimum distance, we must look at the graph Z6 and Z3. The minimum distance of these two graphs is the minimum distance of the quantum code. For example, Z6 has a minimum distance 6 and Z3 has a minimum distance 3. And the quantum code has minimum distance of 3. Also, another way to finding minimum distance, if you look at the graph, we have a triangle with the cycle 3. And the shortest cycle is represented as a minimum distance. And so our minimum distance is 3. And for finding dimension, we must firstly calculate the Hx and Hc transpose matrices as here that we can find, and the H or dimension, K or dimension is the n minus rank of Hx minus rank of Hc, that is 2. And totally we have 12 to 3 quantum code from this construction. And here is the main result. If we consider 2 Cayley graph and then calculate the balance product between them, we can see that we have a linear distance and linear dimension. That in the next slide, in this slide, we have a numerical result. We have some quantum codes from this construction that we can see that if we have a linear distance and a linear dimension, that is a good result in quantum error correction. And we can find a good quantum code as follow. Also, here is my simulation. I use the BPOST algorithm for this simulation. In this simulation, we can see that after some physical error rate, for example, the green line, we don't have any logical error rate. Or in the green line also, we can see we don't have after this part, this error rate, physical error rate, we don't have any logical error rate. That is a good result in the quantum LDPC code and quantum error correction that we have, and it is due to linear distance and linear dimension that we have a good quantum codes. Thank you so much for your attention.
I have a question. So when you go back, you had in your main result slide, you had a lot of codes. One forward.
Here?
Yeah, this one here. So you have a lot of options here. Which one do you think is the best in terms of maximizing the distance, but also having a lot of logical qubits? Or at least the ratio of logical to physical is high enough. Which one, what do you think would be a good implementation here?
For implementation, if we have a higher qubit for implementation, we have better performance. For example, for 12 to 3, the logical error rate is higher than of 2994 quantum codes. If we have a higher qubit that if for implementation needs many times and need many quantum hardware for implementation. But if we have a higher qubit, higher n, our performance and logical error rate is very low.
So
it depends on qubit.
Yeah, so the number of qubits that you show, it's a physical number that it's within the reach of neutral atoms. Have you thought of trying with experimentalists if they can try some of these codes and see if they can do something, at least to test them?
Yes. I test 3 of the codes for decoding part to see a logical error rate. Generally, since we have, for example, 12 to 3, we have 2 type of logical qubit, because the dimension of logical qubit 2 divided 12 into 2 logical qubit, and we send two logical qubit to the algorithm to find the logical error rate. And after simulation, we must find the logical error rate for some physical error rate that happen in the quantum circuit.
Okay, thank you. You also have a question from online. Can you describe your experiment setup? I think these are simulations, right? You're not actually, these are all simulations you're doing here, right? These not actual experiments, right?
Here?
Yeah, so these results, can you maybe go over this quickly again? I think that was,
For this result, firstly, for this simulation, we must find parity check matrices of the quantum code, for example, HX and HC. And for each quantum code. And we must send these parity check matrices to the BPOST algorithm to find physical logical error rate. For this simulation, firstly, we must define physical error rate, because when we have a circuit, we have some part of the noise and we make some error and define it as a physical error rate. And after simulation, we must look at what's happening for logical qubit that we send in the circuit. That the error that we can see comes from logical error rate. Logical error rate is related to logical qubit that we send to the circuit. And when we send some qubit, some error to this algorithm, we can see that, for example, for the green line, we don't have any logical error rate after some physical error rate. That means that we don't have any error in the after decoding part.
Thank you. Thank you.